Oh, hi. Welcome to FROST, the Frankfurt Robotics Science team at the Frankfurt University of Applied Sciences in Germany. We and the rover Eros are ready to show you what we have prepared over the last months. Let's head inside. Follow me.
Hi, my name is Yeldrik and I'm part of the leadership triad at FROST, together with Lukas and Adrian. Historically, FROST has been one of the smaller teams competing at the ERC, so we're more than happy that we've managed to increase our team size to 7 core members, plus an additional 15 regular members. But let's hear from our team who they are and what they're working on.
Hi, I'm Lukas. On the rover, I'm working on general system integration, the energy system and on our robotic arm.
My name is Masud. Currently, I'm working on the gripper and on the ground station.
Hi, I'm Max. I'm responsible for basically every movable part on a rover and also manufacturing.
I'm Luis. I'm working on the energy system and camera intelligence.
We are Maike
and Maria, and we work with cameras,
giving our drone and rover their sight.
I'm Anosh, and my responsibility is the acquisition of scientifically interesting liquids.
Hi, my name is Mats, and my task is to improve the internal hardware structure of our rover.
I'm Philip. And I'm Ivy. We are currently working on our deep drill unit.
Hi, I'm William Gormu. I work currently on the ground station and the LiDAR security features.
Hey, I'm Adrian. I'm the head of drone development here at FROST, amongst other things.
And I'm Lauren, the lead hardware engineer for our new drone and the new frame.
Without the European Robot Challenge, our team would most likely not exist. It not only gives us milestones to work towards, but also projects and opportunities we don't usually have in our student lives. And obviously, we also like to see how we compare against the best teams out there, to learn from them and also to exchange ideas. Eros is our third-generation rover platform, with focus on great capability in the field. At the heart of Eros is a modular drive system, designed for versatility, from outdoor terrain to tight indoor spaces. It features 4 independently driven, steered and height-adjustable wheel assemblies. Each wheel is controlled in 3 degrees of freedom: hub motor, continuous rotation for steering and spindle-based height adjustment. It also features an active digital suspension. Spring and damping parameters adapt in real time to changing terrain.
The rover is powered by a smart, swappable 48-volt battery pack, which feeds the rover energy management and distribution module, responsible for switching, converting and monitoring all power for the rover.
The digital emergency stop operates on multiple levels. The soft stop disables motors while keeping logic and radios running, while the hard stop disables all components. Because of its digital architecture, both can be triggered by the human operator, through the ground station or by the rover itself.
I'm currently working on the new version of the multipurpose tower, for short MPT. It's basically the eye of the rover. It features various components like the antenna, the digital emergency switch, the LiDAR system, and also various cameras. The camera gimbal features a 360 degrees rotational axis and a tilting mechanism. 1 zoom camera to look for interesting stuff around, and 1 wide-angle camera to capture most of the picture.
To supplement the high-fidelity but low FOV gimbal camera, we are currently integrating ultra-wide-angle cameras into our rover to achieve 360 degrees of camera coverage for our machine vision, object and landmark detection, and to act as a panoptical viewfinder.
We have a 6-axis robotic arm, which won us first place in the maintenance task last year. It's built out of an aluminum frame, uses BLDC motors and harmonic drives. All rotation axes use slip rings for infinite rotation. Through these slip rings, we pass power and CAN bus through the arm and to the end effector. On the software side, we can either control each axis separately, or we can use inverse kinematics to move a tool frame on a specific plane. The improvements since last year were mostly software focused. This includes different input methods, like using a space mouse or a gamepad for input, using an improved inverse kinematics algorithm.
The existing gripper is driven by 2 linear actuators. Every finger needs its own power supply. That makes it difficult to synchronize both fingers. That's why we redesigned the gripper. We want to use a 1 rotatory stepper motor to synchronize the movement of the gripper.
To prepare our robotic arm, for more autonomous operations. For example, for tasks like interacting with the maintenance panel, we needed to improve its ability to estimate distances and enable object grasping.
We integrated a stereo camera directly into our end effector. This hardware setup is combined with software for disparity mapping and depth estimation. This allows our rover to obtain 3D information from its environment, giving it and the operator a closer and more precise view of objects during manipulation tasks.
All the before-mentioned cameras serve two purposes. One is enabling a manual operator to control the rover, and the second one is enable autonomous operation. For that we have also added LiDAR sensors that help the rover navigate in a known or unknown map. And we have created a mission planning framework that influences the navigation, the behavior of the robotic arm and various other components. In this mission planning framework, a sequence of operations can be defined. For example, waypoint navigation, or manipulator operation, or any combination of those.
In this year's competition, we want to compete with our next generation drone, Daedalus. The current prototype can be seen here. We want to tell you about the journey that led to Daedalus and present its features. In the previous 2 years, we competed with Icarus, our first generation drone. Icarus served as our test bed for testing sensor concepts, different software and hardware systems, and it helped us to find out what we want in a drone and what we don't want in a drone. Based on Icarus, we were able to develop our autonomy stack, image recognition, and our ground station control software. We were also able to learn many things from Icarus and its failures, and were able to build competency and experience within the team. With Daedalus, we want to take a next step in drone development for Frost. Our goals are to optimize and personalize the system and to create a first modular aerial science platform.
The frame itself gets 80 mm more compact and its footprint is reduced by about 40%. For positioning, we're using an optical flow sensor as a primary system with an RTK sensor as a reliable backup. And on top of that, we have a modular adapter system, so we can mount additional sensors like ultrasonic or LiDAR sensors when a mission calls for it, and remove anything to stay as light as possible when needed.
In this footage, you are seeing a Daedalus prototype testing the new airframe dimensions. You can first see the drone is being armed and started to take off. Afterwards, our pilot can enable the autonomous mission and the drone flies. Finally, we can see the execution of an emergency landing triggered from the ground station.
This is our deep drill unit, DDU. It uses a hammer drill to extract a ground sample, after which it tilts back to deposit the sand into a separate container to be weighed.
For our new DDU, we would like to reduce the weight of the unit by simplifying the deposition mechanism while making sure to reliably extract the deepest soil levels. The science unit uses a peristaltic pumping system because the liquid only touches the internal tubing. This minimizes the risk of cross-contamination whilst maximizing scientific utility. After that, the sample gets put into a sealed containment unit for later analysis. Additionally, we have an onboard sensor that provides us with real-time pH measurements so that we can determine acidity levels before we make regrettable actions.
Calculating best route. You'll reach your destination in 8 days and 17 hours.
All right. See you in Krakow at the European Rover Challenge 2026.